You know, there's a photograph I want to tell you about. It was taken on a clear desert night in 1952 on top of Palomar Mountain in Southern California when an astronomer pointed a 4-8-inch telescope at a particular patch of sky and captured the light from thousands of stars on a single glass plate. Now, photographic plates, and this is the wonderful thing about them, they're remarkably stable. You develop them, you store them carefully, and the image they hold lasts for decades. Centuries even. So that 1,952 photographs still exists. You can pull it out of an archive, hold it up to the light, and see exactly what the sky looked like over California 70 years ago. And here's where things get interesting. A few years back, a team of astronomers, led by a researcher named Beatrice Villarroel, decided to do something rather clever. They took those old photographic plates from the 1950s and they compared them point by point, star by star, with modern digital images of the very same patches of sky, the same coordinates, the same depth, the same exposure, everything matched up as carefully as possible. And what they were looking for, what they really wanted to know, was simple: had anything changed? Now, you might think the answer would be obviously no. The universe is so vast, so ancient, so unimaginably old, that on the time scale of a human lifetime, much less 70 years, almost nothing should change. Stars live for millions, billions, even trillions of years. The light traveling to us has been on its journey for centuries. The thought that something significant could happen in just 7 decades seems, well, almost laughable. But that's not what they found. What they found, and I want you to sit with this for a moment because it really is profoundly strange, was that approximately 100 objects that were clearly visible on the 1,952 plates, objects that looked exactly like ordinary stars, objects that left bright, unmistakable signatures on the photographic emulsion, are now gone. Not dimmer, not moved, not changed, gone. As if someone had reached up into the sky and erased them. So you should be asking yourself the same question those astronomers asked themselves, the question that I, frankly, find utterly captivating. Where did they go? I mean, look, stars are not supposed to do this. Stars are not supposed to just vanish. And here's the critical thing to recognize. When a star dies, when it reaches the end of its life and exhausts its nuclear fuel, it doesn't disappear. It transforms. It becomes something else, something that we can still see, something that announces its presence to the universe in unmistakable ways. If the star is small to medium-sized, you know, something like our sun, it doesn't go out with a bang. It puffs up into a red giant, sheds its outer layers in a beautiful glowing shell of gas we call a planetary nebula, and what's left behind is a hot, dense core, a white dwarf that continues to glow for billions of years. We can see it. It's there. The star didn't vanish. It just changed form. Okay, but what if the star is much more massive? What if it's, say, 10 or 20 times the mass of our sun? Well, that's when you get a real cosmic spectacle. The star runs out of fuel, the core collapses catastrophically, and the outer layers crash inward at a substantial fraction of the speed of light. They rebound off the dense core in an unimaginable explosion. We call this a supernova. And let me emphasize just how bright these things are. A single supernova for a few weeks can outshine an entire galaxy of hundreds of billions of stars. It's the kind of event that, when it happened in our own galaxy in 1054 AD, was seen and recorded by Chinese astronomers, by Native American observers in what's now New Mexico, by anyone with eyes pointed at the sky. The remnant of that supernova is still expanding today. We call it the Crab Nebula, and you can see it through a backyard telescope. So if one of those stars had gone supernova between 1,952 and now, we would know. Everyone would know. There would be no missing it. And if the star was even more massive, say 25 times the mass of our sun or more, then what's left behind after the supernova explosion is a black hole. Now, Black holes themselves are dark, of course. They're, black, but they're not invisible. A black hole near other stars or other gas will draw matter toward itself, and that matter, as it spirals inward, will heat up to temperatures of millions of degrees, blazing in X-rays and ultraviolet light. We see these things. We have telescopes specifically designed to spot them. A black hole forming nearby would not be a silent event. So we have these vanished stars, 100 or so points of light captured on plates in 1952, gone today. And none of them seem to have left any of the expected signatures behind. No glowing nebula where a star died gracefully. No supernova remnant. No new X-ray source where a black hole might be feeding. Just nothing. Empty sky. Now, here's where I have to be honest with you, because this is the responsible thing to do when we're talking about science. The first explanation, the boring explanation, the explanation that any careful scientist has to consider first, is that those old photographic plates might have artifacts on them. Maybe a cosmic ray hit the emulsion. Maybe a piece of dust on the lens caused a fake star to appear. Maybe an asteroid happened to pass through the field of view during the exposure. These things happen. They happen all the time. And in fact, when the VASCO team, that's the name of the project, VASCO, which stands for Vanishing and Appearing Sources, during a century of observations, when they went through their initial list of candidates very carefully, most of the suspects turned out to be exactly that: glitches, defects, things that looked like stars but weren't. The list got smaller and smaller as they applied stricter and stricter criteria. But here's the thing. After all the filtering, after throwing out every candidate that could possibly be explained by an artifact, there remained a residual sample, a handful of objects, maybe a dozen, maybe more. Objects that had bright, clear signatures on the 1,952 plates that looked exactly like ordinary stars and that have no detectable counterpart today, even with telescopes orders of magnitude more sensitive than the ones used in 1952. And these are the cases that are difficult to dismiss. These are the cases that keep astronomers up at night, because in a properly functioning universe, ruled by the physical laws we think we understand, this should not be happening. Now, before we go any further, I want to pause and consider something. Something that I find both terrifying and beautiful in equal measure. Because the truth is, the headline I just spent 10 minutes building up to stars are disappearing is actually only half the story. The other half, the half I think is even more remarkable, is hidden in the title of this video. Something is erasing stars from the sky, and it's getting closer to us. What does that mean? What could possibly be coming toward us, and why should you, sitting wherever you're sitting right now, care? Well, let me back up and tell you a different story. A story that begins not in 1952, but more than 2 centuries earlier, on a cold night in England, when a man named William Herschel pointed his homemade telescope at the Milky Way and noticed something deeply strange. Herschel, was a remarkable character. He started his career as a musician, a composer, and oboist, actually, with a respectable career in Bath, but he became fascinated with astronomy in middle age and ended up discovering the planet Uranus, which earned him a royal appointment and changed the course of his life. He built telescopes larger than anyone had built before. Some of them were monstrosities, 40 feet long, requiring teams of assistants to operate, and night after night, he and his sister Caroline mapped the heavens, cataloging stars and nebula and trying to understand the structure of our galaxy. Now, when Herschel looked at the band of light we call the Milky Way, and I'm sure you've seen pictures of it, that gorgeous river of stars stretching across a truly dark sky, he noticed that it wasn't smooth. It was lumpy. It had bright regions where stars seemed to crowd together, and it had dark regions where stars seemed to be entirely absent. In some places, against the otherwise bright background of the galactic disk, there were yawning gaps, holes, patches of utter blackness, as if someone had taken a punch and removed the stars from those regions. Herschel had a theory about this, and it's worth pausing to appreciate how sensible his theory was, even though it turned out to be completely wrong. He thought these dark patches were exactly what they appeared to be, holes, actual gaps in the distribution of stars. He famously wrote in his notebook, looking at one particularly dark region, "Surely this is a hole in the heavens." And I love that phrase, "a hole in the heavens," because it captures something so human, so intuitive about how we interpret what we see. If you see darkness where there should be stars, the natural conclusion is that there are no stars there. But Herschel was wrong. And he was wrong in a way that took more than 100 years to fully understand. Because you see, those dark patches aren't holes at all. They're not absences. They're not gaps in the distribution of stars. They are, in fact, the exact opposite of an absence. They are the presence of something, something dense, something cold, something that lies between us and the stars beyond, and that blocks the light from those stars completely. What Herschel was seeing, though he couldn't have known it, were dark nebulae. Vast clouds of interstellar dust and gas drifting through the galaxy, dense enough and large enough to absorb the light of every star behind them. Now you might wonder, what do we mean by dust in space? When I say dust, I don't want you to picture the stuff on your bookshelf. Interstellar dust is something a little different. It's made of tiny grains, much smaller than a grain of sand, much smaller even than the dust mites in your carpet. We're talking about particles, maybe a few hundred molecules across, made of carbon, of silicates, of frozen water, and various organic compounds. Each individual grain is essentially invisible. But when you have enough of them, when you have a cloud that's many light years across, containing trillions upon trillions of these particles, they become an effective wall. Light from behind the cloud hits the grains, gets absorbed, scattered, redirected, and what we see on the other side is darkness. The discovery of this fact, by the way, was one of the great surprises of 20th century astronomy. There had been hints earlier, scattered observations that didn't quite add up. But it wasn't until astronomers like Robert Trumpler, working in the 1930s, started carefully measuring the brightness and distance of star clusters that the picture became clear. Trumpler noticed that distant star clusters appeared systematically dimmer than they should have been based on their actual size. Something was sapping the light as it traveled across space. And the more space the light traveled through, the dimmer it became. There was quite literally stuff in the way. This realization changed astronomy. It meant that what we see in the sky is not a clean, unobstructed view of the universe. It means we're peering through a kind of cosmic fog, thicker in some directions, thinner in others. And in the densest patches, the fog becomes opaque. The light from beyond cannot penetrate. Stars that are physically out there, perfectly normal, and presumably shining away, simply cannot be seen from where we are. So here's a question that I want you to hold on to, because it's going to matter as we go forward. If interstellar dust can hide stars from us, can it also, do this in reverse? Can clouds of dust move? Can they drift? Can they shift across the sky over time, revealing stars that were hidden and hiding stars that were once visible? Could that be what's happening with the vanishing stars? Is some dust cloud somewhere out there in our galaxy moving in such a way that it's now blocking the light of stars that used to be in plain view? This is a perfectly reasonable hypothesis. And to assess it, we need to think a little bit about what's actually out there. What lies between the stars in our part of the galaxy? Is it empty, or is it filled with stuff? And if it's filled with stuff, what kind of stuff and how is it arranged? The answer, it turns out, is that the space between the stars is anything but empty. The space between the stars is a vast, complex, evolving ecosystem of gas and dust and magnetic fields and high-energy particles, all of it churning and flowing on enormous scales. We call this collectively the interstellar medium. And the interstellar medium is structured in a way that you would find, I think, quite surprising. Right around our solar system, for a sphere extending about 1,000 light years in every direction, the interstellar medium is unusually thin, diffuse, almost, and I emphasize almost, empty. We call this region the local bubble. And the reason it's a bubble, the reason this region of space is so much less dense than the average patch of the galaxy, is because something blew it clear. Astronomers have pieced together a story that goes something like this. About 14 million years ago, in a region of the galaxy not far from where the sun is now, a series of massive stars reached the ends of their lives and exploded as supernovae. Not just one, but maybe a dozen or more, going off over a period of several million years. The shock waves from these explosions plowed through the surrounding interstellar medium, sweeping the gas and dust outward in a great expanding shell. The inside of that shell got cleared out. The gas became hot and thin and tenuous, and our sun, drifting along its orbit around the galactic center, happened to wander into that cleared out region a few million years later. We're living, right now, inside the cavity carved out by ancient stellar explosions, the local bubble, a hollow in the galaxy's foggy interior. And it's that hollow, that relative emptiness of our cosmic neighborhood, that allows us to see so clearly out into the wider universe. If the sun were located in a denser part of the galaxy, our view of the cosmos would be obscured. We might not even know that other galaxies existed. Now, the local bubble isn't perfectly empty. There's still some gas in here, some dust, just a lot less of it than there would be outside. And there are scattered within the bubble denser pockets, little wisps and tendrils of interstellar material. Some of these are large enough to have their own names. There's the local interstellar cloud, sometimes called the local fluff, and I just love that name. The local fluff, it sounds like something from a children's book, which is a small wispy cloud of slightly denser gas, about 30 light years across. Our solar system happens to be inside the local fluff. We entered it sometime in the last 100,000 years or so, and we'll probably exit it within the next 10,000 to 20,000 years. There are other clouds nearby. There's the G cloud, sitting just beyond the edge of the local fluff in the direction of the constellation Centaurus. There's the blue cloud, the aqua cloud, the airy cloud. There's a whole catalog of these little wisps, each one a slightly denser pocket of interstellar material, all of them drifting through space with their own velocities, their own trajectories. And here is where the story I'm telling you starts to converge. Because the sun is moving, we're not stationary. We're orbiting the center of the Milky Way at about 230 kilometers per second, which is about 514,000 miles per hour. And within that orbit, we have our own peculiar motion through the local environment. We're heading, roughly speaking, in the direction of the constellation Hercules. And as we move, we're not just passing through empty space, we're passing through clouds. We've been in the local fluff for a while now, and we're heading directly into the G cloud. So here's the wonderful kind of unsettling thought. Something is in fact coming toward us, or to be more precise, we're moving toward it. We're going to enter the G cloud sometime in the next few thousand years, maybe sooner, maybe later. It depends on exactly where the boundary is and our exact velocity, but it's going to happen. What will that be like? Well, the G cloud is denser than the local fluff. It's denser than the surrounding bubble. When we enter it, the heliosphere, that bubble of solar wind and magnetic field that surrounds our solar system and protects us from interstellar radiation, is going to get compressed. The boundary that currently extends about 100 astronomical units beyond the Sun, well past Pluto, that boundary is going to move inward. Cosmic rays are going to penetrate more deeply into our region of space. The Earth's atmosphere is going to be exposed to higher levels of high-energy particles than it has been in recent geological history. Now, I want to be clear, because I don't want anyone panicking. This is not, an immediate threat. We're not going to wake up tomorrow and find ourselves engulfed in a deadly cloud. The transition will be slow, gradual, taking place over thousands of years. And the G cloud, while denser than what we're in now, is still much less dense than what you'd find in really thick interstellar clouds elsewhere in the galaxy. Life on Earth has been through similar transitions in the past. We've been in and out of denser clouds many times during the Sun's 4.5 billion year history. Each transition probably changed conditions on Earth in subtle ways, changing the rate of cosmic ray bombardment, perhaps affecting cloud formation, perhaps influencing climate. Some researchers have even speculated that passages through dense interstellar clouds might be connected to ice ages or mass extinctions. But on the timescale of a human life, even on the timescale of all human history, the effects are negligible. But here's the deeper question. The question that brings us back to the mystery of the vanishing stars. Could the things happening in our local cosmic environment, the motion of clouds, the shifting of dust, be enough to actually erase stars from the sky? Could a denser pocket of interstellar material moving across our line of sight to a distant star be enough to make that star vanish from view? Well, here's where I have to give you the honest answer, which is probably not, or at least not in the way we're discussing. The stars that vanished in the Vasco survey weren't slowly fading. They were there in 1952 with their full brightness, and now they're gone. A drifting dust cloud would, generally speaking, cause a gradual dimming, not a complete disappearance. And the timescales for interstellar clouds to move appreciably across our field of view are, in most cases, much longer than 70 years. So dust clouds, the ordinary interstellar medium, probably can't account for the missing stars, which means, and this is where things get really interesting, we need to look elsewhere. We need to consider possibilities that go beyond the standard cosmic fog. We need to ask whether there might be other things out there in the galaxy, things that don't shine, things that don't show up in our normal surveys, things that could move quickly enough or that could intervene strangely enough to make a star simply disappear. And this is where modern astrophysics has been generating some, I have to say, deeply unsettling ideas. Ideas about what might be lurking in the dark spaces between the stars. Ideas about the nature of the universe at scales we have barely begun to explore. Have you ever heard, for instance, of failed supernovae? The standard picture, the one I outlined a few minutes ago, says that when a massive star runs out of fuel and its core collapses, the result is either a neutron star or a black hole, with a brilliant supernova explosion announcing the event to the universe. But what if that's not always the case? What if, sometimes, the collapse happens so quickly, so completely, that the outer layers of the star never get the chance to bounce and explode? What if sometimes a massive star just falls in on itself, quietly, without fanfare? This is no longer a hypothetical question. Astronomers have reported observations of a star in a nearby galaxy, the spiral galaxy NGC 6946, sometimes nicknamed the fireworks galaxy because it produces so many supernovae that it appears to have done exactly this. The star, designated N6946 BH1, was a massive red supergiant, about 25 times the mass of our Sun, and astronomers had been monitoring it for years. In 2009, it briefly flared in brightness, glowing brighter than normal for several months, and then it disappeared. Not just dimmed, disappeared. Subsequent observations with the Hubble Space Telescope and other facilities failed to find it. The star was just gone. The interpretation that astronomers have settled on, tentatively, is that we were watching a failed supernova. The core of the star collapsed directly into a black hole without the usual explosion. A small burst of energy escaped during the collapse. That's the brief flaring, but most of the star's matter fell straight into the new black hole. The result is a black hole sitting where a star used to be, surrounded by no expanding remnant, accompanied by no supernova fireworks. To the eye and to almost any of our telescopes, the star simply vanished. Now, here's why this matters for the missing stars in the Vasco survey. If failed supernovae are a real phenomenon, and the evidence is growing that they are, then we expect a significant fraction of massive stars to end their lives this way. Maybe 10%, maybe more. And every one of those stars will, in essence, disappear from our view, leaving behind a black hole and not much else. If you were running a survey of the sky, comparing images from decades apart, you'd see these stars vanish, just like the Vasco team did. So that might be part of the answer. Some of the vanished stars in the survey might be failed supernovae, massive stars that collapse into black holes without putting on a show. And the truly fantastic thing about this, the thing that makes me genuinely excited as a physicist, is that it means we have a new way of finding black holes. Not by detecting the X-rays they emit when they accrete matter, but by watching for the absence of stars that used to be there. A kind of negative space astronomy. Looking for things by looking for what's not there. But, and you knew there was a but coming, not all the vanished stars in the Vasco survey can be explained this way. Failed supernovae should only happen to the most massive stars, and those are rare. The candidates in the Vasco survey include objects that appear too faint to be massive stars, things that look like more ordinary, more sun-like objects, and ordinary sun-like stars are not supposed to collapse into black holes. The physics just doesn't allow it. They simply don't have enough mass to overcome the quantum mechanical pressures that would, keep them stable as white dwarfs or neutron stars. So if some of these vanished objects aren't massive stars undergoing failed supernovae, and if they're not dust clouds passing in front of them, what are they? What could possibly explain a sun-like star disappearing without a trace, without a remnant, without a single photon left behind to tell the story? And this is the question that I find truly thrilling, because to answer it, we may need to consider possibilities that take us into the deepest, most speculative corners of modern physics. We may need to talk about objects that have been theorized but never confirmed, about forms of matter that we suspect exist but have never directly detected, about possibilities that frankly sound more like science fiction than science fact, but that careful researchers are now treating with deadly seriousness. We may need to talk about primordial black holes, about dark stars, about the possibility that the dark matter that makes up most of the gravitational mass of our galaxy is not, as we've long assumed, some kind of exotic subatomic particle, but is instead made of much more ordinary sounding objects, objects that could in principle drift through space, occasionally passing in front of or even consuming the stars we observe. We may need to talk about things that by their very nature we can never see directly, things that betray their presence only through their gravity, their absence, the holes they leave behind in our view of the cosmos. And we may need to talk about the unsettling possibility that some of these things are not safely far away, off in the distant reaches of the galaxy, where they can't affect us. Some of them may be quite close. They may be in our cosmic neighborhood. They may, in fact, be passing through the local bubble right now. They may, in some sense that I'll explain in just a moment, be heading our way. So here's where I want to leave you at the end of this first part of our journey, with a sense of the puzzle we're trying to solve, with a feeling for the strangeness of it, and with a hint of what's to come. Because in part 2, I want to take you deeper into this mystery. I want to talk about a class of objects that physicists have theorized for half a century. Objects that could be lurking in the dark spaces of our galaxy by the millions. Objects that, under the right circumstances, could move through space in ways that would make stars vanish before our eyes. I want to introduce you to a kind of cosmic detective work that combines gravitational lensing, microwave background observations, and high-precision astrometry to hunt for things that should be invisible. And I want to tell you about a discovery made just within the last few years that has raised the possibility that we are not, in fact, alone in the local bubble, that we share this little cleared out region of the galaxy with companions we cannot directly see, companions that move on their own trajectories, companions that may, on a long enough time scale, drift through our region of space. Something, you see, really is erasing stars from the sky. And there is, I think, good reason to believe that the agents of this erasure are not always far away. They may be much closer than we'd like to think. And one of them, if our calculations are right, and they may not be maybe slowly, silently, inexorably heading this way. So when you look up at the stars tonight, I want you to consider the possibility that the sky you see is not the same sky that your grandparents saw, and it is not the same sky that your grandchildren will see. The universe, even on a human time scale, is in motion. Things are appearing, things are disappearing, and the cosmic dark, as we will discover, may not be quite as empty as it appears. So we'd arrived at this rather unsettling point where ordinary explanations, dust clouds drifting across our line of sight, failed supernovae quietly swallowing massive stars, well, they could account for some of the vanished objects in the Vasco survey, but not all of them. And the ones they couldn't account for, the residual mystery, are the cases that should keep us up at night. Because the implication, the thing that the data seems to be telling us, is that there might be other things out there, things we've theorized about for decades, but never directly observed, things that could, in principle, hide stars or even consume them and leave us scratching our heads at empty patches of sky. So I want to take you now into one of the most beautiful and, frankly, one of the most counterintuitive ideas in modern physics. An idea that goes back to the 1960s, that has been worked on by some of the most brilliant theoretical physicists of our time, including Stephen Hawking himself, and that has, in the last few years, undergone something of a renaissance. I'm talking about primordial black holes. Now, when most people think about black holes, and you've probably heard about black holes plenty by now, they're everywhere in popular science, they think of them as the end states of massive stars. A star much heavier than our sun runs out of fuel, collapses, explodes as a supernova, and leaves behind a black hole. That's the standard story, and it's a correct story as far as it goes. Those kinds of black holes, the stellar mass black holes, definitely exist. We've observed them in binary star systems for decades. We've directly imaged them with the Event Horizon Telescope. We've heard their collisions through gravitational waves. They are, in this sense, well-established residents of our universe. But here's the thing. Stellar collapse is just one way to make a black hole. And it turns out that in the very earliest moments of the universe, in conditions so extreme that they make a supernova look like a candle, there may have been an entirely different mechanism for forming black holes. A mechanism that operated long before the first stars existed. A mechanism that could produce black holes of any mass, including masses that are completely impossible for stellar collapse black holes to have. Let me back up and explain what I mean. We have very good evidence that the universe began about 13.8 billion years ago in a state of extraordinary density and temperature. The Big Bang, is the standard term for it. though it's a somewhat misleading name because it wasn't really a bang in the conventional sense. It was more like an expansion of space itself, starting from a state where everything was packed together in a way that defies our normal intuitions. And in those first fractions of a second, the universe was so dense and so hot that the physics was nothing like what we experience today. Quantum effects dominated. Pressure and temperature were unimaginable. Energy density was such that in places the conditions for gravitational collapse could occur on absolutely tiny scales. Here's the idea, in essence. The early universe wasn't perfectly uniform. There were tiny fluctuations in density, ripples in the primordial soup, regions that were slightly more dense than their surroundings. Most of these fluctuations were small. They grew over billions of years, eventually seeding the structure of galaxies and clusters and the cosmic web. But occasionally, by sheer statistical chance, a fluctuation might have been large enough in a small enough region to trigger immediate gravitational collapse. That region of unusually dense primordial matter would simply fall in on itself right there in the first second after the Big Bang and form a black hole. Now, the wonderful thing about this mechanism, and the reason it's so different from stellar collapse, is that it doesn't require the black hole to be very massive. A stellar collapse black hole has to be at least about 3 times the mass of our Sun, because below that mass, the quantum mechanical pressures inside a neutron star are strong enough to prevent collapse. But primordial black holes have no such restriction. They could be as small as an asteroid or as massive as a galaxy. They could have any mass at all, depending on the exact size of the density fluctuation that gave birth to them. And here's where it gets really interesting. If primordial black holes formed in the early universe, and if they had the right range of masses, they could still be around today. They wouldn't have evaporated because Hawking radiation, the slow leakage of energy from black holes that Stephen Hawking famously discovered, only matters significantly for very small black holes. A primordial black hole more massive than about 1 trillion kilograms would, survive the entire age of the universe without losing a meaningful fraction of its mass. It would just keep doing what black holes do, sitting there, lurking, pulling on things gravitationally. And here's the kicker. Here's the part that has the astrophysics community in such a state of intense interest right now. Primordial black holes, if they exist in sufficient numbers, could account for some or all of the dark matter in our galaxy. Dark matter, as you may know, is the invisible stuff that makes up about 85% of all the matter in the universe. We know it's there because we can see its gravitational effects on galaxies, on the rotation curves of stars, on the way light bends around clusters, but we have never directly detected what it actually is. For decades, the leading hypothesis has been that dark matter is some kind of weakly interacting particle, something exotic from particle physics. But despite 40 years of searching with increasingly sensitive detectors, no such particle has ever been found. And so, in recent years, the idea that dark matter might be made of primordial black holes has come roaring back. Maybe what we call dark matter isn't some mysterious new particle at all. Maybe it's just a vast population of small black holes formed in the first second of the universe, scattered throughout the galaxy, invisible because they're black but present in enormous numbers. Now, take a moment with this. Think about what it would mean if dark matter is primordial black holes. Then our galaxy isn't just a collection of stars and gas. It's also a collection of black holes, vast numbers of them, drifting between the stars, moving on their own orbits around the galactic center, mostly small, perhaps the mass of a planet or a small moon, but black holes nonetheless. The space between the stars isn't empty. It's, populated. It's populated by objects that we cannot see directly, that interact with normal matter only through gravity, and that on rare occasions must pass close to the stars and gas that we can see. You can probably see where this is going. If primordial black holes exist, and if they make up some significant fraction of the dark matter, then occasionally, not often, but occasionally one of them is going to pass directly in front of or even into a star. And what would that look like? Well, the answer depends on the mass and trajectory of the black hole and the size and density of the star. But the possibilities are genuinely strange. If the black hole is small and passes through the outer layers of a star quickly, it might leave the star largely intact, just punching through with relatively little disturbance. But if the black hole is more massive, or if it gets captured by the star's gravity, it might settle into the core. It might begin to slowly consume the star from the inside out. The star would continue to shine for a while, but it would gradually lose mass, becoming dimmer and dimmer until eventually the entire star would be drawn into the black hole. And then, well, what would we see from Earth? We'd see a star that fades and then disappears without any of the usual signatures of stellar death. No supernova, no planetary nebula, no expanding cloud of debris, just a star, there one decade, gone the next. Does that sound familiar? Does that sound perhaps like exactly the kind of thing that Vasco has been finding? Now look, I want to be careful here. The hypothesis that some of the Vasco objects are stars being consumed by primordial black holes is, highly speculative. There are many things that have to be true for this picture to work out, and we don't yet have direct evidence that any of those things are true. But the possibility is real enough, plausible enough, that astrophysicists are actively investigating it. And that in itself is remarkable. But I want to take this further, because there's another aspect to the primordial black hole story that I find genuinely thrilling. And that aspect is that if these things exist, they should leave detectable fingerprints even when they're not consuming entire stars. They should produce subtler effects. Effects that we have in the last few years started to look for in earnest. The most beautiful of these effects is something called gravitational microlensing. Now, the basic idea behind gravitational lensing comes straight out of Einstein's general theory of relativity. Mass curves space, and light